Now, unlike odd power functions, even power functions are not one-to-one, but we still want to have a way to somehow reverse them. We still want a way to say what number raised to this power gives us this result. So we define a partial inverse. We did this very informally with the absolute value. We're much more formal now that we're talking about these power functions. For a positive even integer, we define the pth root function to be the function so that its inverse is x to the p with the domain restricted to positive numbers or 0. So if we take our U-shaped or N-shaped curve and we get rid of all the stuff to the left of 0, what we're left with is 1-to-1. And so if we take just the half of our U-shaped or N-shaped curve, just the half where the input is positive, we get something with an inverse, and that's the pth root. In other words, the xth root of p is the unique non-negative real number whose pth power is x. Non-negative means positive or 0, right? The root of 0 is just 0. If we want to have the negative root, the negative number that raised to the pth power gives us x, we just slap a negative sign on that. Now, the domain and range of even roots is more interesting than the domain and range of odd roots. For odd roots, it was just all real numbers. For even roots, however, well, our power function, we restricted the domain. We restricted the domain of x to the p to contain only the non-negative numbers, so 0 to infinity, which means that the range of the even root is just non-negative numbers. The output of an even root is always positive or 0. And then the range of the even power function already consisted of non-negative numbers. And so the domain of the even root also consists of non-negative numbers. So that's for the base even root function. The domain is positive numbers, the range is also positive numbers, and in both cases that they include 0. How do we find the domain and range of any old radical function? Well, we use the domain and range of the base radical, and then we reason with inequalities. Right, so here we have 3 times the 6th root of the quantity 6 minus x plus 1. So we know that the 6th root has input and output both greater than or equal to 0. So for the domain, we have 6 minus x greater than or equal to 0. So we solve that inequality. We'll subtract 6 on both sides, negative x greater than or equal to negative 6. We'll divide both sides by negative 1, which requires reversing the inequality. So x less than or equal to 6. The domain of this function is x value is less than or equal to 6. So negative infinity up to 6, and 6 is included. We also know that the 6th root has output greater than or equal to 0. So our 6th root here is greater than or equal to 0. What's happening to that in this function? Well, it's being multiplied by 3, so I'm going to multiply both sides by 3. So now I have 3 times the 6th root is greater than or equal to 0. And then after it's multiplied by 3, it's having 1 added. So now I have 3 times the 6th root plus 1. is greater than or equal to 0 plus 1 is 1. So the range of this function consists of everything greater than or equal to 1. So 1 up to infinity. So what did we do to figure out the domain and range here? We thought about the base function, and then we reasoned with inequalities. To find the domain, we had to solve. To find the range, we had to manipulate. Right? We started with the sixth root by itself, and then we put in all of the things that are happening to it. Now, of course, in addition to finding the domain and range of the radical functions, we can do the same things that we did for odd roots with even roots. So we can find the values of even roots by trial and error. So we want to find the fourth root of 16. 1 to the fourth is 1. 2 to the fourth, and that's 16. So that means the fourth root of 16 is just 2. We want to find the second root of 25. Well, we might know this just as an arithmetic fact, right? 5 to the second power is 25, which means that the second root of 25 is 5. Now, wait a minute. The second root? Yeah, we'll talk about that in a minute. Finally, we're asked to find the fourth root of negative 81. But wait, negative 81 is not in the domain of this even radical. In other words, there's no real number whose fourth power gives me something negative. So we say the fourth root of negative 81 is undefined. So it's not, this is some irrational number that we can't write down. We mean there's no number like that. On the other hand, just like with the odd roots, even roots are frequently irrational numbers as well. At which point we have exactly the same options that we did with the odd roots. Leave it alone, decimal approximation on the calculator, rough approximation by hand, simplify it, which we'll talk about later.